Hey, chemistry class. I wanted to make a quick video to show you a couple things about the salts and solubility simulation that I have asked you to play around with over the weekend. Um, and so here we go. Like I said in our Zoom meeting today, I think this is a really great simulation, and it helped me have a concrete understanding of some things that are happening on a molecular level that are really hard otherwise to sort of gain a concrete understanding. So we'll take a look at how this works and hopefully let you play around on your own to get a better sense. So if you open the program, we're on a tab by default that's table salt, that is NaCl, sodium chloride. And you've got this salt shaker that you can shake, and it drops crystals of sodium chloride, table salt, into this very tiny volume of water. The volume, 5 times 10 to the negative 23 liters. This is just an incredibly minute volume of water. And sodium chloride is a highly soluble ionic compound. Salt is another word for an ionic compound. So table salt is that particular salt, that particular ionic compound that we keep on our table, shake on our food. And we see that the quantity of sodium chloride that I've shaken in here has dissolved completely. There are separate sodium ions and chloride ions, the red sodium ions, the green chloride ions, bouncing around in this volume of water. If you watch closely, every once in a while, you'll see a sodium and a chloride ion sort of stick together because, well, they are opposite charges and they're attracted to each other. But in solution, they're also very strongly attracted to the water molecules that are all around them. The chloride ions with their negative charges are going to be strongly attracted to the hydrogen parts of water molecules because those hydrogens are partially positive. And those positively charged sodium ions are going to be very strongly attracted to the partially negative oxygen parts of water molecules. And so ionic compounds like sodium chloride dissolve because those partial positive and partial negative parts of the water molecules will get into the crystals of the ionic compound and separate those individual ions from one another. And once they've sort of surrounded an ion, they keep it from reconnecting with other negative or positively charged ions, the opposite charged ions. So we've got a bunch of sodium chloride swimming around here, and it's all dissolved. Sodium chloride is very soluble, and that means that the bonds between the water molecules and the ions are quite strong, and they sort of override the already strong attractions between the positive and negative ions in the crystals of sodium chloride. And if I keep going, eventually I will get so much sodium chloride in the solution that the crystals just fall down to the bottom. Now, at this stage, we would say that the solution is saturated. It is holding as many of the free ions as it possibly can. And we have at the bottom a chunk of solid sodium chloride. But this is a dynamic equilibrium, a changing equilibrium. And if you look closely, you will see that this crystal at the bottom of our little volume of water is constantly changing, with ions breaking off as water molecules from the solution surround them and break them off of that chunk, and ions reattaching to the crystal because there's so many ions swimming around here that having a positive ion bump into the crystal at a place where there's a negative chloride ion and having them stick together is also happening quite often. And the rate that the ions are breaking off and the rate that the ions are rejoining the crystal are now exactly the same. So we have this dynamic equilibrium, this changing situation of constancy. And if you look up here in the top right corner, you see that the numbers of dissolved ions and the numbers of bound ions in this crystal are fluctuating a little bit, but they're always right around that 180, 181 for the dissolved, 38 or so for the bound crystals, bound ions. Now, you may notice in the minute or so that I've been talking here that the crystal has changed shape. And that is because this is a dynamic equilibrium. It's changing. All right. So we're going to look at now a slightly soluble salt. And if you click on that tab at the top of the simulation, you see on the right there is strontium phosphate, but that's a drop-down menu. And you can choose from any one of these 6 different slightly soluble ionic compounds. All ionic compounds will dissolve at least a tiny, tiny bit in water. But some of them, like the slightly soluble salts in this simulation, dissolve so little that it seems like they are not soluble at all. And you'll see what I mean in a minute. One thing to notice up front, the volume here is much greater. The size of the tank looks the same, but the volume is much greater. 1 times 10 to the negative 16th liters. That is 2 million times more water than was in the previous container. And we need that much greater volume of water because these ionic compounds are so much lower in their solubility. They dissolve so much less in water that if we don't have enough water, we can't get any to break off the crystal, more or less. So let's see what it looks like if I shake in some strontium phosphate into our volume of water here. Well, there are quite a few ions that have broken off of the crystal. We have about 46, 47 ions of each, of the strontium, and about 30 of the phosphate. Strontium is 2 plus, phosphate is 3 minus. So the ratio in the compound is 3 to 2. So not surprisingly, we have a 3 to 2 ratio of ions that are dissolved. But look at all the ions that are remaining in the crystal at the bottom of the tank. And remember, there are only 40-something dissolved here, and the volume is 2 million times greater than in the previous simulation with the sodium chloride. So how much dissolves with strontium phosphate compared to sodium chloride? It is virtually none. It is so small an amount. Millions of times less dissolving going on in this case. But the same thing is happening. We have this dynamic equilibrium with the ions breaking off and rejoining the crystal at equal rates, so that over time, the amount of dissolved and the amount of bound ions is constant. So I'm going to leave you with that, and I'm going to just go ahead, like I always do when I open this simulation, and just be a little bit hypnotized and mesmerized by the molecular activities that happen. All right, I hope you have fun playing with this, and we'll talk about it when we meet again next week. Have a great weekend.